Hi, my name is Hasan. I will be presenting our work on uncovering the operation of in-DRAM RowHammer protection mechanisms. Let's start with a summary. The RowHammer vulnerability of modern DRAM is a critically reliability and security threat. Today, DRAM vendors implement target row refresh, or TRR, in their DRAM chips. TRR is an obscure, undocumented, and proprietary RowHammer mitigation technique. Due to their proprietary nature, the security guarantees of these RowHammer mitigation techniques cannot be easily studied. In this work, our main goal is to answer the following questions. Is TRR fully secure? How can we validate the security guarantees of different TRR mechanisms? To this end, we propose UTRR, a new methodology that leverages data retention failures in DRAM to uncover the inner workings of TRR and study its security. At a high level, UTRR performs two steps. First, UTRR profiles the data retention time of a row R. Second, UTRR finds when the TRR mechanism refreshes row R and builds an understanding of the underlying TRR mechanism. Using UTRR, we analyzed 15 DDR4 DRAM modules from each of the three major DRAM vendors. Through this analysis, we make several observations regarding the TRR mechanisms implemented in these modules and craft new custom RowHammer access patterns that evade the TRR mechanisms and cause RowHammer bit flips. Our results show that, first, all 45 modules that we test across three vendors are vulnerable to our new RowHammer access patterns. Second, our access patterns cause at least one bit flip in almost all DRAM rows in many modules. This makes system-level RowHammer attacks easier to mount, as the attacker would have the ability to cause bit flips in almost any DRAM row. Third, we observe that our access patterns cause up to 7 RowHammer bit flips in an 8-byte data word, making ECC ineffective and systems equipped with ECC also susceptible to RowHammer attacks. We believe UTRR will facilitate future research by leading to the development of more secure RowHammer protection mechanisms. This is the outline of today's talk. I will start with describing some DRAM basics. Here, I show a typical system with a CPU and a DRAM module that has several DRAM chips. Inside the DRAM chip, there are multiple banks, which contain many DRAM cells organized as a two-dimensional array. A DRAM cell stores a single bit of information as electrical charge. In a bank, the cells are vertically connected to sense amplifiers, which can read the data from the cells and update it if needed. And cells are organized horizontally as DRAM rows. Now let's look at DRAM commands that the memory controller issues to access the DRAM. To perform access, the memory controller first activates or opens a row by issuing an activate command. The activate command loads rows data into the sense amplifiers where the data can be accessed. After the row is accessed, the memory controller issues a precharge command to close an open row so that a new row can be activated. This is basically how DRAM is accessed. Each DRAM cell stores data in a fundamental leaky capacitors. Here's a simplified diagram of a DRAM cell where the capacitor in red stores the data and the access transistor gates access to the data. There are a number of leakage paths by which charge can enter or exit the capacitor. The important thing to note is that stored data can be corrupted if too much charge leaks, which is the same as saying if the capacitor voltage degrades too much. Here we have a simplified diagram of the capacitor voltage over time. We see that the voltage decreases over time in an exponential decay. There's a threshold Vmin under which we can no longer guarantee that we will correctly read the data that was originally stored in the cell. As long as a cell's voltage remains above this line, we consider this a retention success. However, as soon as the voltage drops below Vmin, we consider this a retention failure. In order to prevent failures from charge leakage, known as retention failures, periodic refresh operations are issued to recharge the capacitor voltage. The intervals between refresh commands are referred to as the refresh window. Now I will tell you about RowHammer and the main RowHammer protection mechanism implemented in DRAM chips today. In order to access data from a DRAM row, say row 2, the memory controller first opens or activates the row. After all requests are serviced from row 2, the memory controller must close or precharge the row in order to begin accessing data from another row. Due to an increase in cell-to-cell interference as a likely result of increased cell packing density, rapidly activating and precharging a DRAM row can result in bit flips in nearby rows. Continuing to access the same row results in even more failures in nearby rows. This phenomenon is known as RowHammer. We refer to the rapidly accessed row as an aggressor row, and the rows containing bit flips as victim rows. To protect their DRAM chips against RowHammer, DRAM vendors currently implement proprietary RowHammer mitigation mechanisms typically called target row refresh or TRR. The key idea of TRR is to refresh nearby rows upon detecting an aggressor row. We demonstrate how TRR operates at a high level. The TRR mechanism detects an aggressor row as a result of rapidly activating and precharging the same row. To protect the neighbor victim rows from experiencing RowHammer bit flips, TRR refreshes the victim rows by performing TRR-induced refresh operations. TRR refreshes victim rows by piggybacking TRR-induced refreshes to the refresh commands that the memory controller periodically issues. Although this is how TRR operates at a high level, different vendors implement TRR differently, and the exact operation of these TRR mechanisms is unknown. Therefore, TRR is obscure, undocumented, and proprietary. Because of this, today, we cannot easily study the security properties of TRR and make sure it is fully secure. Our goal is to study in-DRAM TRR mechanisms to understand how they operate, assess their security, and secure DRAM completely against RowHammer. I will now present our methodology for uncovering the TRR operation. We propose UTRR, a new methodology to uncover the inner workings of TRR. The key idea of UTRR is to use data retention failures in DRAM as a side channel to detect when a certain row is refreshed by TRR. UTRR consists of two main components, row scout and TRR analyzer. Row scout finds a set of DRAM rows that meet certain requirements as needed by TRR analyzer and identifies the data retention times of these rows. TRR analyzer uses the rows that row scout provides to distinguish between TRR-induced and regular refreshes, and thus builds an understanding of the underlying TRR mechanism. I will describe the two components of UTRR in more detail. The goal of row scout is to identify a list of DRAM rows which must be useful for TRR analyzer, and the retention times of these rows. Row scout must find rows with consistent retention times. This is critical for UTRR to correctly infer whether or not a row has been refreshed by a TRR-induced refresh operation. Row scout must find DRAM rows whose retention time do not change over time due to variable retention time or VRT effects. Row scout must also find multiple rows or a row group that are located at certain configurable distances and have the same retention time. This is required so UTRR can observe whether or not a TRR mechanism can refresh multiple potential victim rows at the same time. I will now explain the row scout operation using a flowchart. First, row scout searches for DRAM rows that have retention time T. Row scout profiles the retention time of a DRAM row by simply initializing a row with known data patterns such as all ones and measuring for how long the row correctly retains its data without being refreshed for the time interval T. Step 1 outputs addresses of rows with retention time T, which is initially set to a small value, for example 100 milliseconds, with the aim to minimize how long UTRR experiments take. This is because the time that UTRR experiments take largely depends on the retention times of the rows that row scout finds. Second, row scout puts together rows that have certain row address distances among them, as indicated by the configuration parameter we call row group layout. Here's an example of a row group that has 3 rows indicated by V that are 1 row address apart. Depending on how many rows are found in step 1 and how many of them can be combined to match the row group layout, step 2 outputs a set of candidate row groups. Next, if the candidate row groups are fewer than needed, row scout increases T by a certain amount and returns to step 1. If the candidate row groups are enough, row scout repeatedly profiles the retention times of the rows in the candidate row groups for many iterations. This is to verify that all rows in a row group have consistent retention times and do not experience variable retention time effects. Candidate row groups that have consistent retention times are output as row groups, and the rest of the candidate row groups are discarded. If the number of retention time verified rows is not enough, row scout returns to step 1 to find rows with increased retention time T. These steps are repeated as I explained until row scout finds a sufficient number of row groups, and finally row scout outputs a list of the retention profile rows to be used by the TRR analyzer. I will now describe the operation of TRR analyzer. The goal of TRR analyzer is to use row scout provided rows to determine when TRR refreshes a victim row. At a high level, TRR analyzer operates in 3 steps. It runs a certain DRAM access pattern, or we can call it a RowHammer attack. Second, TRR analyzer monitors the retention failures that row scout provided rows experience to determine when TRR refreshes any of these rows. Third, based on when and which of the row scout provided rows are refreshed by TRR, the user develops an understanding of the underlying TRR operation. I will now describe a general TRR analyzer experiment. As the first step, TRR analyzer initializes the retention profile rows with known data. In this step, TRR analyzer also initializes the aggressor rows that the user can specify to hammer on later steps of the experiment. The user specifies aggressor rows in locations relative to the retention profile rows. For example, assume a row group with 3 retention profile rows denoted as victim rows using V, where the victim rows are one row apart. The user may specify an aggressor row between the first two victim rows. Hammering the aggressor row would mostly disturb the two victim rows immediately adjacent to the aggressor row. This is called single-sided row hammer. Or the user can specify two aggressor rows to perform double-sided row hammer as shown, and hammering both aggressor rows would disturb all three victim rows while having the greatest effect on the middle victim row. Second, TRR analyzer performs a set of operations to reset the internal state of the TRR mechanism so that it isolates the experiment about to be run from the prior experiments that could have potentially changed TRR's mechanism state. This step is optional, and we provide more details in the paper on why this step is sometimes needed and how we reset TRR's internal state. If TRR analyzer does not activate any of the victim rows for their profiled retention time t, we expect to see bit flips due to retention failures in these rows once we read their data back. In order to make TRR perform a TRR-induced refresh operation, the DRAM has to receive a refresh command. TRR analyzer issues refresh commands when the victim rows are not refreshed for half of t. This is to ensure that the victim row retains its data correctly until it is potentially refreshed by TRR-induced refresh. And similarly, it correctly retains its data after a TRR-induced refresh until TRR analyzer reads source data. To analyze how accessing the aggressor rows affects the rows that TRR detects as aggressors, TRR analyzer activates some precharges or simply hammers the aggressor rows. By hammering an aggressor row with individual hammer count, TRR analyzer can understand how the hammers affect the decisions of TRR on which rows to refresh. Along with the aggressor rows, TRR analyzer can also hammer dummy rows to analyze how to make the aggressors undetected by TRR. A dummy row is simply a randomly selected row in the same bank that is not an aggressor or a victim row. TRR analyzer provides various configuration parameters to study different access patterns. We discussed these parameters in our paper. Overall, the TRR analyzer user understands how a certain TRR mechanism operates based on when the TRR mechanism refreshes which of the retention profile rows. I will now describe the observations we made by analyzing existing TRR mechanisms using UTRR and explain the new RowHammer access patterns we crafted. To implement UTRR and conduct the DRAM experiments, we use SoftMC, an FPGA-based DRAM testing infrastructure. We modified SoftMC to support DDR4 modules. We use SoftMC because it provides fine-grained control over DRAM commands, timing parameters, and temperature. In our study, we analyzed 15 DDR4 DRAM modules from each of the three major DRAM vendors. In the paper, we have a table that provides detailed information about the tested modules, and here's a glimpse of the table. Let's look one by one at the key observations we make regarding each vendor's TRR implementation. In this talk, I will omit the details about how we used UTRR to make these observations, but you can find those in the paper. I will also talk about one particular TRR mechanism from each vendor, but we found small differences in the TRR mechanisms of modules manufactured at different times by the same vendor. Let's start with vendor A. Vendor A performs three types of refresh operations. It performs a regular refresh that every DDR4 DRAM does. In addition, the TRR mechanism performs two variations of TRR-capable refresh commands. We refer to these as TRF1 and TRF2. In this timeline, each tick represents a refresh command that the memory controller periodically issues. During the first 8 refresh commands, the DRAM chip performs a regular refresh operation. On the 9th refresh command, the TRR mechanism performs TRR-capable refresh TRF1, which I will explain shortly. The next 8 refresh commands are again used to perform regular refresh, and they are followed by TRF2. Overall, the TRR mechanism uses every 9th refresh command to perform TRF1 and TRF2 in an interleaved manner. Let me explain the difference between TRF1 and TRF2. We suspect that vendor A's TRR implements a counter table to keep track of repeatedly activated potential aggressor rows. The table has 16 entries, where each entry contains a row address and a counter value to indicate the accumulated hammer count of the corresponding row. When performing TRF1, the TRR mechanism refreshes the neighbor rows of the row ID that corresponds to the largest value in the table. On the other hand, TRF2 uses a pointer that indicates the row ID from the table to refresh its neighbors. After performing TRF2, the TRF2 pointer advances to the next entry in the table in a circular manner. Based on these observations, we craft new RowHammer access patterns that circumvent the TRR mechanism of vendor A. Our approach in crafting a RowHammer access pattern is to aim for having the attacked aggressor row discarded from the counter table prior to a DRAM refresh command. With this, our goal is to let TRF1 and TRF2 pick any other row from the counter table, but not the aggressor row that we actually hammer, such that TRR cannot refresh this row. To this end, we craft the following access pattern. Immediately after a refresh command, we hammer two rows A1 and A2 that are one row apart to perform double-sided RowHammer attack. We hammer each row n times. Then, to discard A1 and A2 from the counter table, we hammer 16 different dummy rows n plus 1 times each. By hammering the dummy rows more than the aggressor rows, we make the TRR replace A1 and A2 in the counter table with the dummy rows. The maximum value of n depends on how many hammers can be performed during the time interval between two refresh commands. Doing so, we prevent the TRR mechanism from detecting the aggressor rows, since both TRF1 and TRF2 can detect a row from the counter table, which contains only dummy rows. To execute this RowHammer access pattern, it is important to synchronize the accesses with the refresh commands to perform aggressor and dummy row hammers at the right time. We conclude that one can circumvent vendor A's TRR mechanism by discarding the actual aggressor rows from the counter table by sufficiently hammering a set of dummy rows. Now, let's look at vendor B's TRR operation. Different from vendor A, here we observe a single type of TRR-capable refresh. We observe that TRR-capable refresh commands are more frequent than those in vendor A. A TRR-capable refresh happens on every fourth refresh command. We make two key observations regarding how the TRR mechanism of vendor B operates. First, TRR probabilistically samples the address of an activated row as a potential aggressor row. Second, a newly sampled row overrides the previously sampled one, even if the neighbors of the previously sampled row were not refreshed by a TRR-induced refresh yet. These two are the most relevant observations, but in the paper we present more observations that helped circumvent the TRR mechanism of vendor B. Basically, a TRR-capable refresh command targets the row address that has been last sampled by the TRR mechanism. This mechanism seems to assume that an aggressor row will be activated frequently enough such that TRR will sample the aggressor row with a high probability, even if the probability of a single activation being sampled is relatively low. To circumvent the TRR mechanism of vendor B, our approach is to maximize the probability of having a sampled dummy row by hammering a dummy row as many times as possible before the subsequent TRR-capable refresh. After a TRR-capable refresh command, we start with hammering the aggressor rows A1 and A2. Because the TRR mechanism could have sampled one of the aggressor rows, TRR could detect one of them if it gets the chance to perform a TRR-capable refresh. At this point, we hammer a dummy row many times in order to get the TRR mechanism sample another row activation and override the previous sample, which potentially includes one of the rows A1 and A2. As we hammer the dummy row more, we increase the probability of having the dummy row sampled and detected by the following TRR-capable refresh. We sweep the hammer counts n and m to find the values that maximize the RowHammer bit flip count. In conclusion, one can circumvent vendor B's TRR by overwriting a sampled aggressor row by making the TRR mechanism sample a dummy row prior to a TRR-capable refresh command. Let's move on to vendor C. Vendor C performs regular refresh and one type of TRR-induced refresh. Every 17th refresh command is TRR-capable. Based on our analysis, we suspect that this TRR mechanism is more sophisticated compared to the other two vendors. It potentially uses a combination of both counter-based and sampler-based approaches. However, we make two key observations that helps us craft an effective RowHammer access pattern. We observe that TRR detects a row across only the first 2K row activations. Row activations performed after the first 2K activations await the TRR mechanism. We also observe that rows activated earlier within the 2K activation commands are more likely to be detected by TRR. Basically, TRR probabilistically detects an aggressor row within the first 2K activations while favoring the earlier activations more. To circumvent the TRR mechanism of vendor C, our approach is to first activate dummy rows to maximize the probability of making TRR detect the dummy row instead of the aggressor rows that we hammer later. In our access pattern, after TRR-capable refresh, we first hammer a dummy row. Then we hammer the two aggressor rows A1 and A2 until the next TRR-capable refresh. The aggressor rows are less likely to be detected than the dummy rows, especially when we first perform a large number of dummy hammers. In conclusion, one can circumvent vendor C's TRR by first hammering dummy rows to make the actual aggressor rows less likely to be detected by TRR. Now I will present the RowHammer bit flips that our new access patterns cause. Leveraging the understanding we developed using UTRR, we craft new RowHammer access patterns that circumvent the TRR mechanisms of three major DRAM vendors. We evaluate the effectiveness of these patterns on 45 DDR4 DRAM modules, and we find that the new RowHammer access patterns cause a large number of RowHammer bit flips. Let's look at the effectiveness of our new RowHammer access patterns at DRAM row granularity. The plot shows for each of the 45 modules we test the fraction of rows that experience at least one RowHammer bit flip compared to all rows in a DRAM bank. We find that all 45 modules we tested are vulnerable to our new RowHammer access patterns. Further, in 20 of the modules, our RowHammer access patterns cause bit flips in almost all of the rows. But why are some modules less vulnerable? We find that it is because of three main reasons. First, some modules are fundamentally less vulnerable to RowHammer, in the sense that rows in these modules can tolerate a higher number of hammers before experiencing RowHammer bit flips. Second, some modules implement a different TRR mechanism that our custom access patterns are not as effective. We believe understanding those different TRR mechanisms more can help to craft more effective RowHammer access patterns. Third, some modules of vendor C implement a unique row organization that appears to mitigate RowHammer at the DRAM circuit level. We conclude that, although some modules are less vulnerable, our access patterns successfully circumvent the TRR implementations of all three major DRAM vendors. The new RowHammer access patterns cause a lot of RowHammer bit flips, but can conventional DRAM ECC protect against those bit flips? This is a simplified diagram of a DRAM module with ECC. In this example, in addition to 4 DRAM chips that store data, a fifth chip stores redundant ECC data. Each chip provides 16 bits or 2 bytes of data per cycle. A 2-byte data chunk is called a symbol. All data symbols constitute an 8-byte data word, and all symbols, including the ECC symbol, constitute a 9-byte code word. The memory controller uses its ECC engine to decode incoming code words. When there are bit flips in the code word, conventional DRAM ECC can correct a single bit, or it can be designed to correct a single symbol. The ECC engine can detect 2-bit errors or 2 symbol errors, and the ECC engine cannot correct or detect 3 or more bit or symbol errors. Now let's analyze the RowHammer bit flips at a smaller granularity and see whether ECC can protect against RowHammer bit flips that our access patterns cause. This plot shows, individually for each DRAM vendor, the distribution of 8-byte data chunks that have 1 to 7 RowHammer bit flips. The y-axis is in log scale. The majority of the 8-byte data chunks are those that have only a single RowHammer bit flip, which can be corrected using typical sected ECC. However, our RowHammer access patterns can cause at least 3 bit flips in modules of all 3 vendors. Further, we see up to 7 bit flips in many data words, which the sected ECC cannot correct or detect. We conclude that conventional DRAM ECC cannot protect against our new RowHammer access patterns. In our paper, we have more observations regarding how the TRR mechanisms of the 3 vendors operate, a detailed description of the RowHammer access patterns we crafted, a sensitivity study on how the number of RowHammer bit flips change when we sweep the number of hammers per aggressor, observations and results for individual DRAM modules, and more. Let me quickly conclude my talk. The RowHammer vulnerability of modern DRAM is a critical reliability and security threat. The security guarantees of TRR, which is the commonly used RowHammer protection mechanism, cannot be easily studied, as TRR is obscure, undocumented, and proprietary. In this work, our main goal is to answer the following questions. Is TRR fully secure? How can we validate the security guarantees of different TRR mechanisms? To this end, we propose UTRR, a new methodology that leverages data retention failures in DRAM to uncover the inner workings of TRR and study its security. Using UTRR, we analyzed 15 DDR4 DRAM modules from each of the 3 major DRAM vendors. Through these analyses, we make several observations regarding the TRR mechanisms implemented in these modules and craft new custom RowHammer access patterns that cause RowHammer bit flips in TRR-protected DRAM modules. Our results show that, first, all 45 modules that we test across 3 vendors are vulnerable to our new RowHammer access patterns. Second, our access patterns cause at least 1 bit flip in almost all DRAM rows in many modules. This makes system-level RowHammer attacks easier to mount, as the attacker would have the ability to cause bit flips in almost any DRAM row. Third, we observe that our access patterns cause up to 7 RowHammer bit flips in an 8-byte data word, making ECC ineffective and systems equipped with ECC also susceptible to RowHammer attacks. We conclude that TRR does not provide security against RowHammer and can be easily circumvented using the new understanding provided by UTRR. We believe and hope that UTR will facilitate future research by enabling rigorous and open analysis of RowHammer mitigation mechanisms, leading to the development of both new RowHammer attacks and more secure RowHammer protection mechanisms. Thank you for your time. I'm happy to receive any questions online or via email. We invite you to read our paper for much more information.